Hello and welcome to the Subsidence Lab activity. This lab is from Investigations in Environmental Geology, but I've modified it and updated some of the figures a little bit. And so here we go. Here's the introduction. Subsidence, or sinking of the land surface, is a hazard commonly associated with resource extraction. Subsidence has been attributed to several factors, including decline of hydrostatic pressure in oil and water producing zones due to withdrawal of fluids, underground mining, solution and compaction of soil by irrigation water, oxidation of organic materials, and formation of sinkholes by collapse of bedrock in karst regions. Some of the more spectacular examples of subsidence are those related to sinkhole development, such as that of May 1981 in Winter Park, Florida, and collapse into abandoned underground coal mines in eastern Ohio, Youngtown area, Pennsylvania, and Rock Springs, Wyoming. The objective of this exercise is to investigate the causes and hazards of land subsidence associated with fluid withdrawals. Some well-known areas of subsidence due to fluid withdrawals include oil fields in Goose Creek, Texas, Long Beach, California, and Lake Maracaibo, Venezuela, gas field in Niigata, Japan, and the Po Delta, Italy, and groundwater reservoirs near Houston, Galveston, Phoenix, Las Vegas, Mexico City, Tokyo, and the San Joaquin and Santa Clara valleys in California. We will be focusing on the Santa Clara Valley in California later on in the lab activity. The magnitude of the problem is illustrated by the following statement. Subsidence in the San Joaquin Valley probably represents one of the greatest single man-made alteration in configuration of the Earth's surface in the history of man. It has caused serious and costly problems in construction and maintenance of water transport structures, highways, and highway structures. Also, many millions of dollars have been spent on the repair of replacement of deep water wells. Subsidence, besides changing the gradient and course of valley creeks and streams, has caused unexpected flooding, costing farmers many hundreds of thousands of dollars in recurrent land leveling. With increased need for the resources extracted from the subsurface and increased human use of the surface, the problem of land subsidence can be expected to increase. Part A. Land subsidence due to groundwater extraction. The causes of subsidence by water withdrawals are related to the compressibility of rocks and sediments and their contained water, but mostly just the sediments. When the water level is lowered by pumping wells, water not only drains from the aquifer but is also squeezed from the fine-grained confining beds or clay layers. The withdrawal of water, which may be under considerable pressure, may lead to subsidence because the reduction of hydrostatic pressure results in compaction of the compressible aquifer and the confining beds. The volumetric reduction is exemplified by subsidence, or lowering of the ground surface. When wells, tapping a confined aquifer, remove water from the sand and gravel of the aquifer, a widespread reduction in the water pressure in the aquifer and an increase in the load on the aquifer's framework commonly results. The increased load on the aquifer framework of sand and pebble grains causes the decrease in volume, or compaction. But this decrease may be stopped or even slightly reversed, very slightly reversed, if the fluid pressure is increased enough to cause the aquifer to return to its original shape. Thus, the aquifer portion of the unit behaves in a nearly elastic manner. But once it collapses, usually it doesn't re-expand or uncollapse. Usually once it's collapsed, it's pretty much collapsed. A large part of the compaction and the surface subsidence is due to the behavior of the clayey confining layers. The amount of compaction or volume reduction depends partly on the type of clay present in the confining beds. For example, the clay mineral montmorillonite may contain more water in its structure and be more porous and compressible under a given load than clay composed mainly of the mineral illite or kaolinite that may contain less water in their structures. The chemistry of the clay the texture of the sediment, and the overburden load, so how much is on top of the aquifer, also affect the reduction of volume and therefore the amount of subsidence. And so there's a couple questions on aquifer characteristics. So this is, what to expect of a clayey silt. Is it a good aquifer or is it a confining bed? And let me tell you, it's not a good aquifer. And then it asks about what is a confined aquifer. And there's a good example of it in Figure 1, which we're going to talk about in a little bit. So Part B addresses subsidence in the Santa Clara Valley in California. The Santa Clara Valley was the first area in the United States where land subsidence due to groundwater pumping was recognized. As of 1971, subsidence has stopped due to a reversal of the water level decline. Yay! The valley is a large structural trough filled with over 1,500 feet of alluvium, or sediments that have washed in from mountains on either side. It includes the lower part, the semi-consolidated Santa Clara Formation, deposited in the Pliocene and Pleistocene, so a while back, but not that far ago, or long ago. Sand and gravel aquifers predominate near the valley margins, but the major part of alluvium is fine-grained, i.e. small-sized sediments like silt and clay. Below a depth of 200 feet, the groundwater is confined by layers of clay, except near the margins. And I'll show you Figure 1, and we'll talk about confined aquifers. Initially, wells as far south as Santa Clara flowed to the surface without the aid of a pump, which is called an artesian well. But decline in water pressure caused the wells to no longer flow to the surface. The decline in water pressure occurred due to pumping for agricultural purposes, 90% of water use until about the mid-1930s, and 18% in 1967, which is a critical time when subsidence was reversed. By 1960, well, maybe not reversed, halted. By 1965, the artesian head had declined 150 to 200 feet within most of the confined area. The decline was not continuous. Recharge of the aquifer occurred between 1938 and 1947, in part because of controlled surface water infiltration into subsurface aquifers. Most of the wells tapping the artesian system range from 500 to 1,000 feet in depth, so pretty deep wells, although a few reach to 1,200 feet. Well yields in the valley range from 500 to 2,500 gallons per minute, which is pretty substantial. So there's several questions here that refer to several figures, and I'm going to show you the figures. I kept them in a different file, so you'll have a PDF file of these figures. Hopefully it won't be too confusing to have two files open at once, but I think it should be good. This is Figure 1, which shows the groundwater system of the Santa Clara Valley. And you can see here you have recharge areas where surface water can percolate into the ground. And these are over here by the mountains on either side. And then in the middle of the valley, we have several extensive clay layers in the aquifer itself. And so the aquifer here, the water here, feels the elevation pressure from over here where it recharged. So when you drill a well into this aquifer here, the water is going to be pushed up by the pressure it feels over here. It's going to be pushed up to the surface if there's enough pressure. And there was at the beginning of well drilling. So several wells flowed. The water just pushed up the well because it felt the pressure over here in the groundwater recharge area. Now these artesian wells only occur in confined aquifers. So these clay layers are impermeable. Water doesn't go through them. So water here can't go through these clay layers. And also water from up here doesn't go through. But the water here doesn't go through the clay layers, so it can build up this pressure so that when a hole is punctured through the clay layer or a well is drilled, the water can push up through it, making these artesian wells, these wells that flow. So a confined aquifer is an aquifer that it's isolated from the atmospheric pressure in that area. And the isolation occurs because of these confining clay layers. The aquifer over here in the recharge area is not confined, which is great because here water will go down into the subsurface. If it was a confined aquifer here, water wouldn't get down deep into the subsurface. And so here is just a normal aquifer, open to the surface. Water can recharge into the ground. And here is a confined aquifer where the water is isolated from surface pressure by these clay layers. So confined aquifer, and over here is unconfined aquifer, where the surface water can recharge the groundwater at depth. Okay. Here is another figure very similar to the next figure, figure 2 and 3, but this is from this is water level decline from 1934 to 1960. And this is water level decline from 1934 to 1967. And that difference of 7 years is pretty critical. There's quite a bit of subsidence going on. So these contours are how much the ground has subsided. So this contour here is 4 feet. So between 4 and 5 feet in here, that's how much the ground subsided during the time period 1934 to 1960. You go to the next slide and you can see that the numbers are slightly higher. So here is a 6 and here is a 7 contour. So in here the ground has subsided between 6 and 7 feet in the time period 1934 to 1967. Next image, we see a well casing that's been damaged, which is kind of cool. And here is a poor photograph taken in 1914. I guess they didn't have excellent photography back in 1914, but we can see sea level has changed between 1914 and 1978 here at the Yacht Club at El Viso. And then this is a change in water level at a well in San Jose, California. So this is water level feet above and below land surface. And this LS is the land surface. And you can ignore this part here. This is subsidence in feet. Originally in the activity you were supposed to graph subsidence in feet on this graph, but here in this image it's already done for you. So here's a land surface subsiding. And in the background, this blue line is depth to water, feet below land surface. And then the black line here is total groundwater pumpage. And then here we have imported water used for recharge. And that recharge happens in the regular unconfined aquifers near the mountains. And then finally here is table 1. You can get some data off of it to answer one of the questions. So back to here. There's 22 questions that you get to answer before you take the lab quiz, the Subsidence Lab quiz. I think the lab is fairly straightforward and not too difficult, but of course that's me, not you. So if you have any questions, do feel free to email me. And if you're excited about the Santa Clara subsidence problem, there's a couple fun resources here that I grabbed some of the pictures, the updated pictures from. So hopefully this lab is fun and informative, and good luck.